I'm not sure if we'll start soon. Oh, there it goes, recording, top left. There you go. All right, welcome everyone to Orchestructure. Thanks for coming. We know the weather has been not awesome and it's still coming down. So thanks especially to Richard. We had 50 people sign up and only a few people showed up. So thank you very much for being true Michiganders and doing that. We have pizza, we have drinks. We obviously have way too much pizza, so take a box with you if you want. Help us get rid of it or do whatever. Anyone have any announcements or anything before we get started? So we've had people ask for gRPC introductions for a long time. So we had asked April at Google, she could help link us up with someone. And today is actually the 5th birthday of gRPC being open source by Google. So woo, congratulations, all that good stuff. So what we're going to do is we'll let him do his presentation, last questions. Of course, we're going to be recording this and streaming it for the people who weren't able to make it. And with that, Richard, take it away.
Great, thank you so much. So my name's Richard Belleville. Thank you for inviting me here. I am at Nossen on most things, GitHub and Twitter. So today I'm going to be taking you through the basics of writing a simple application, client and server, in gRPC and Go specifically. So this is going to be based on the code in a repo that I have linked here. So you can go there and look after the fact. My slides don't have complete detail, but after the fact, you can go back and look at everything as much as you want. So first, a little bit about myself. I was actually born and raised in Brighton, Michigan, not too far from where you are right now. I left when I was about 12, though. Went to the University of Alabama, graduated 2016, spent 2 years working at a networking company called Adtran, working on cloud native network orchestration. So it'd be like, the idea is you could deploy something to Kubernetes or similar that allows you to turn up fiber service at somebody's house without anybody coming out in a truck and actually, turning things on. I've been here for about 1.5 years now. I'm a developer on the gRPC team. I work mostly on Python, and I've got a focus specifically on usability, at least recently. So disclaimer, I'm not an expert in Go. I asked Jorge before this meetup what language he thought people would be interested in or know very well, and Go was the answer, and that makes sense for a group called Orchestructure. So I've tried to tailor things to that. This is actually based on a talk I originally gave at GBG San Francisco based on Python. So one thing that's actually kind of nice about this is it demonstrates the interoperability of gRPC. The clients and servers from the original Python presentation are interoperable with the clients and servers that we're going to build today. Okay, so let's get started talking about gRPC. So usually when I ask people if they've heard what gRPC is, they can take a stab at it and guess, hey, it's Google RPC, right? That only works if they've ever heard what RPC is. So since this is kind of a small group, I'm going to try to be a little bit interactive. Raise your hand if you heard about gRPC. Cool. Raise your hand if you know what RPC is. Okay, so most of you. Cool. To give a really quick overview, because people are much more familiar with messaging systems these days. Messaging systems tend to include stricter semantics on top of just a networked connection. RPC stands for remote procedure call. So you make something happen on a potentially different machine, right? REST, though, has semantics about like cacheability and about how things mutate other things. You can actually have a RESTful RPC service if you provide those semantics on top of your RPC-based API. So what about gRPC in particular? We are multi-language. We handle a lot of different languages here at Google, and I know I have a face for each language that you might name. And then there are also community built wrappers for other languages, like I've seen Haskell, I've seen Rust. Swift is maintained by somebody else. It's pluggable, so authentication is pluggable. You can build your own new authentication system and plug it right into gRPC in basically every language. But we also have defaults, right? So we'll handle OAuth, we will handle SSL. At Google, we have our own in-house authentication authorization. Tracing. So most languages have a concept of middleware. They're called interceptors. So you can add in your own tracing if you want. Zipkin, Jaeger, Open Census is most common here. Custom resolver. So you could use DNS. We have some more complicated name resolution mechanisms that you could use instead. We've got load balancing. So this doesn't necessarily mean a proxy load balancer. More often with gRPC, you use something more complicated called a look-aside load balancer, where there's no proxy involved at all. Now, the really big thing is the interface definition language, what we'll get to later. Just know that's pluggable. Multi-platform will run on basically everything, and that's actually a real headache for developers on the team because it takes a lot of effort to maintain every platform in the world, and it takes even more money to run tests on all of the platforms. And feature-rich, bidirectional streaming, flow control, binary logging. So I wanna zoom in on just a couple of these here. I'll come back to this slide in just a second. So what does the basic flow look like when you have gRPC running? Well, the idea is you want a function that you would otherwise run on the same machine to run on a different machine. And you want it to look as much as possible without abstracting away too much information. You would like it to look like it's running on a local machine, right? So you write a client, and that client has a stub, which corresponds to the function. It invokes a function on the server, it runs on the server, and it returns a response. Okay, this is like an HTTP client and server pair. I'm sure you're familiar with this sort of flow. So what is interesting about gRPC? Okay, so let's talk about protocol buffers, because I think that's the number one biggest value proposition for gRPC is a strong schema for the data that you pass from your client to your server. So this looks a lot like a struct you might write in, say, C. You have messages, which are like a struct, and they have fields. So we can say a point has a latitude and a longitude, and we're going to encode that as a 32-bit integer. There's an equal sign here, which includes a field number. Now, for each field, that number must be unique, but it can change over time. Now, protocol buffers have a wire specification. That means that this thing will always encode to a fixed series of bits on the wire. And there are bindings for protocol buffers in pretty much every language that you can think of that is highly performant. People focus very closely on making sure that serialization and deserialization of protocol buffers is performant. But the important thing is that this provides a way to do backwards compatible changes to your API. Right? So say somehow there were a third new value that got added besides latitude and longitude on the Earth. I don't know how that's possible. Maybe we add a new dimension or something like that. It is still wire compatible to add that third field. As long as you ensure that you don't do anything stupid on your servers, you can continue using those new messages with old servers, and they'll just throw that field away. Okay, so that's what we call the interface definition language. Technically speaking, gRPC is agnostic to the interface definition language. But what we do is we will generate code for your protocol buffers that knows how to do serialization and deserialization. So let's go to the next part. Also inside of your protocol buffer, you can write a service. A service looks a lot like a function definition, right? So you've got a route guide, which has 3 methods, 3 RPCs, get feature, taking a point, latitude and longitude, and returning a feature. Let's just start there for the moment. This point refers to a message definition earlier in your proto file. And the feature, well, it's a message that's not specified in this slide. But if you go into any of the gRPC repos, you can see this exact route guide feature. This is implemented for every single language that we support. So gRPC will write bindings by default in your language. It will generate code that you can then pull in as a library that allows you to do something equivalent to just calling a get feature function, just calling a list features function, just calling a record route function. And those functions will take in protocol buffers, and they will return protocol buffers. Now, since it is agnostic to the interface definition language, you could potentially pull out protocol buffers and use, say, JSON instead. But that's an advanced use case that would probably take a little bit more doing. Okay, so there's another interesting bit here in this slide, which is this second method here has this keyword stream. Okay, so gRPC features full bidirectional streaming. So we talk in terms of client-side streaming, server-side streaming, and then the opposite of streaming is unary. So we would just call this a unary RPC. We would call this a server streaming RPC, and we would call this, well, this one is a client streaming RPC. Okay, so you ask for a rectangle, and that's like, you know, a rectangle of latitude and longitude, and we can stream back features to you, and you can run your code concurrently. You can process those features concurrently. It doesn't just return a list of features all as one response as you might get in traditional HTTP. And that's another big value proposition here, is you can actually do concurrent streaming, concurrent APIs. And later on in this talk, we're actually going to use streaming to, I think, pretty good effect. Okay, there are a lot of other add-ons, and they might just distract at the moment, but you can go and look in the repo to see all of the other features that we provide. Control plane functionality is a really big deal for gRPC that you don't have in many other traditional messaging services. Okay, so let's talk about the architecture for different languages real quick. So there are 3 major parallel implementations of gRPC. There is gRPC core, which is written in C++. There's Go, which we'll be talking about today. There's Java. And then a lot of other languages are thin wrappers on top of core. In terms of transport, generally, we build on top of HTTP2. That decision was made to allow greater interoperability on the wider internet. A lot of custom protocols are blocked in routers and when you have like deep packet inspection. So that enables greater usage throughout the wider internet. A lot of RPC systems like these tend to just be fenced into data centers. The intent is that gRPC can be used not just in the data center, but on mobile devices and to make requests into a data center. Okay, so that's a lot of stuff. Let's try to make it more concrete. So we're going to write an application using gRPC in Go. So this is a really, really simple data structure, and I'm sure it's one that you've written before. We're going to be writing an in-memory key value store. Okay, so think maybe like a very, very simple version of Redis. So we'll keep a map in memory. We'll give you the ability to create a new key value pair. You can update an existing key value pair, and you can get the value associated with a given key. Okay, so here is what our protocol buffer definition looks like. And you can go and look at the full .proto file in the GitHub repo. So we have a record, which contains a name and a value, both strings. We have, so let's skip over the request for a second. We have a get record method, like I just mentioned, a create record method and update record method. So here I wrap the record, in create record request, I wrap a record. In general, you want to have a wrapper around any internal protobufs for each request so that it gives you space to independently update in a backwards compatible manner the request as you need to, right? So say in the future, I needed some other field here in create record request, like say I wanted to do an upsert instead, and I wanted to add a flag here. Well, I can now add a bool flag in create record request without modifying the record. Otherwise, you would have problems where there are a lot of special casey things on the record. There are best practices for how to write protobuf defined APIs, and Google Cloud has published those as I think they're called AIPs. So you can go ahead and take a look at those. But in general, it actually is a good idea to, when possible, write things in a RESTful manner. RESTful as defined by Timothy Berners-Lee and not as defined by people who call HTTP plus JSON REST. Okay, so we've got get, create, and update. So an aside, you wrote this protocol buffer, right? How are you going to share these between different applications? A lot of people have come up with different answers to this. The answer traditionally in Google is to have a monorepo, so you can just refer to your protocol buffer as a location in a big directory. People outside don't tend to have monorepos, right? You'll have lots of tinier Git repos. So people will do things like Git submodules. So their organization will have one Git repo that holds all of their protocol buffers, and they can reference one another. And then they just use a Git submodule. This is a fine solution. Sometimes you can use a language level package manager, right? So suppose you know that your organization is only going to use Java. You could publish your protos and their generated code as a Java package, and Java does do that. You could even use like a simple HTTP file server to pull them down. One thing that a lot of people do, which isn't a best practice, is to generate your code from your protocol buffers and your service definition, and then check it into source control. So there are some problems here. One is getting out of sync, right? So suppose since ideally this is going to be shared by multiple repos, otherwise what's the point? Your distributed system. Somebody's going to update the protocol buffer in one repo, and they're not going to update it in the other one. And then you might get version skew, which could lead to bad things. That sort of thing has led to outages in the past here. So just a good thing to be aware of. And this is an example of how you might achieve that, for example, in Python. It turns out not to be as much of a problem in Go. Okay, so here's the data structure that we're actually going to be using in Go. And when you think about it, all that we're doing is offering networked access to this data structure, which is a string map and a little bit of extra stuff here for synchronization. So you can really just ignore all the fields except for M at this point. And there's a link here. I will make this slideshow available after the presentation so that you all can go back and look to it. But if you want to like look at it in parallel, let me go back to the first slide. Here is the repo, github.com/nosin/kvd. So nosin/kvd. Okay, so let's start by writing the get record method. It turns out to be pretty simple. Actually, let me open this link. Okay, so we generated code in our repo available here, and we call it PB. That is the generated protocol buffer code. Let me give you a quick look at what that looks like. So here's our proto file that we just talked about. We generated code from it, and we get something that looks like this, right? So let's see if we can find get record. Okay, so that's the client. Let's find the server. Okay, here's the server. So we have a key value store server here, and you can see the interface that it creates for it, right? So we're going to take in a Golang context. We're going to take in a pointer to a get record request protocol buffer, and we're going to return a pointer to a record protocol buffer and an error. And that maps pretty much one-to-one to what you've got in your .proto file over here, right? So relatively simple. You need to make that import happen. And I think that should give you the context to understand what's happening over here. So the locking is important because you're going to have one Go routine per request incoming to your server. So you need to make it safe for concurrent access, right? We first do a very simple check to see if the key is already in the mapping. And if it is, if it's not, since we're doing a GET request, then we want to fail it, right? So we have a system of error codes that you can return back. These are gRPC level error codes, not HTTP2 level error codes. For the most part, they map to the system of error codes that Google has been using for a very long time. So actually, maybe quick aside for a history lesson, Google has been using RPC since I think like 2003. And the system internally was called Stubby because you have stubs and you have servers, right? So the Stubby team worked really hard on the concurrency model for Google since then. And then I think it was around 2014 the team decided that they wanted to create something that is open sourceable, right? You probably know that like Kubernetes came from Borg, which was developed at Google internally. This is the same sort of idea. We needed something that was open sourceable and not intimately tied to a bunch of infrastructure at Google. That's how gRPC started. But you will still see some remnants of experience from Stubby that don't necessarily match up with what other people are doing when it comes to networked communication. So what it really comes down to here is we get a value from our mapping, and then we return a record protocol buffer with it populated with the request name and with the value for that name. Relatively simple. You also have to know how to start up a server listening on a particular port, right? So you use net.listen, that's relatively standard. You create a new gRPC server, and you create your new servicer for it, our key value store, which we defined over here. And then you register your service with it and you start it up. So also relatively simple boilerplate. We already looked at the generated server code. And I already talked about our server concurrency model. You should know that concurrent reads from a stream are unsafe and concurrent writes to a stream are unsafe. Okay, so there should always be a way to manually interact with your microservices. If you're using HTTP, you probably will use something like curl or Postman, and that same sort of tooling exists for gRPC. So I've been I have been promoting gRP curl recently, which wasn't written by Google. It was written by a guy called Joshua Humphreys, who I think works at a company called Full Story. Most of the time, you won't actually need to write a client yourself, right? You can just use gRP curl. So later on in this talk, we are going to be building a client just to show you how to write client code. But if you just want to build a server and deploy it, you don't necessarily need to write that. Or you could write the client in another language. One thing that's important is with curl or Postman, usually you're using JSON, which is human readable. Protocol buffers on the wire are a binary format. So that is a little bit more difficult. They also need to know how to serialize what you write, right? You write something human readable here. So you'll notice here that I don't point gRP curl at the protocol buffer file, right? We're actually using JSON as the human readable format here, but this is a gRP curl invocation to create a record. And then we see we created foo with value 1. Relatively simple. I should also say, to cut some corners here, to save time on building the example, I did make this plain text. I'd recommend that you not do that. Please secure your servers with SSL or with TLS rather. But for the moment, this example does use plain text. And you have to explicitly include a call with insecure. So not a best practice to do that. So here we're not including a path for where you should look for the protocol buffers. And that's because we did something on our server back here. Okay, so there is a protobuf or a Golang module called reflection, which allows you to say, I want to add a new service to my server besides just the key value store one that will allow you to query me for what protocol buffers I use and what methods I export, right? So what happens when I use gRP curl here is it says, hey, I don't have protocol buffer definitions. I don't fundamentally know how to turn this JSON into a serialized protocol buffer message. So what it does is it queries the server to see if it has reflection. And if it does, it gets all of that information back and it becomes just as easy as using curl. But it's faster and it's strongly schema'd. So I would recommend in like staging or for debug, you have reflection exported on your server. You may not necessarily want this when you put it into production. It certainly makes it much easier for debugging. The alternative is you include an extra flag in your invocation that says, hey, here's where my protocol buffers are. Please parse them. All right, so now let's talk about writing a client. It's also relatively simple. We first need to create a request. right? So we have a get record request, which includes the name, the key that we're looking for. We are using a client that's passed in to us, which you need to create, and we can go to the code for that. But you just call client.getRecord, you pass it a context, you pass it your request, and you get a value back. It really is very much just like calling a function. You have to first set up your client, which encapsulates information like what server am I talking to? So we should take a look at that code real quick. Create. Pull this out to a different file. All right, so to create a client, you call gRPC.dial with perhaps a little bit more configuration. I think I'm using with insecure here. And then you can just use your client, client.create, that sort of thing. Okay. So this is part of the generated code for a client, and this is the interface for the client, right? You've got a get record, which you can call create record, update record, and then watch record we'll talk about in a second. Okay, so raise your hand if you're confused right now. No? Okay, cool. Maybe a loaded question. So I want to talk a little bit about testing the services. We have sort of an interesting philosophy to testing relative to what I was used to when I came here. The big thing is we actually don't like using mocks. We find that using mocks tricks you into thinking that you have tested something that's actually going into production, but oftentimes you'll find that your mocks don't really match up to what's going to happen in production. So we like to include both a client and a server, very small in terms of memory footprint, in the same process, spin them up, have them actually use networked communication over localhost. And that should be fast, deterministic, and production-like. We aim for having tests that run for only a few seconds and that fail less than one time per 10,000 runs. And we achieve that, I think, relatively well. So single process if you can. If not, multi-process, single node, and multi-node if you hate yourself. If you just start by pushing things to Kubernetes instead of running a local unit test, that's probably going to be a bad time. Another thing that you should know is ports are shared state. So if your test uses a single static port, that's a singleton instance, right? You can't run multiple instances of that test. Okay. So there's a test file here as well that gives an example of what that style of testing might look like, just to give you an idea. Okay, so we went through simple unary RPCs, things that are single request, single response. Let's now talk about something a little bit different. So you're probably used to the idea of polling in traditional HTTP APIs, right? So you initiate some action that's going to run for a long time, and then you poll on some URI that gives you the status of it. Since gRPC is based on the idea of streams, you can simply maintain a TCP connection. Instead of polling, get pushed a change when it happens, which usually people will write their own custom TCP protocol for. So we're going to add that. You're going to add a watch on a key, and you will get streamed back changes to that particular key. Okay, so here's what our watch record looks like. This is, by the way, this is a client unary server streaming RPC. Okay, so here is the implementation on the server side of our watch method. We're going to add a watcher. We're going to defer removing a watcher. And then we're going to have an endless loop until cancellation. We will pull things off of a channel, which is provided by our watcher, and then we'll send them on the stream. So let's suppose that you just wanted to stream back the numbers 1 to infinity. What you could do is, like, while true, stream.send I, something like that. And this is backed by a channel under the hood. And then your client will be able to iterate over those. We do use the Golang context to show when something has been canceled on the client side. So this here allows you to not leak a Go routine and to finish gracefully when the client hangs up. Say your client hits Control C, then that would be handled by this case. So there's a little bit of synchronization behind this, and you can go look at the full code to see what that's about. Client implementation. So on the other end, what does it look like? How do you iterate over the stream of results? So again, here as well, we have an endless loop, and we use stream.receive. That's the fundamental element here that you need to know about. And we just print out the records as they come. Okay, so everybody good so far? Haven't lost anybody? Okay, cool. And so this is the last part, and there's not a ton of stuff here, but I want you to know that gRPC services absolutely do work in existing cloud providers. So as a proof of concept for that, I did spin up real quick KVD, the key value server that we've been building here on GKE. Relatively simple. Create a cluster, you get credentials for it, you create a deployment with the image that you build. There's a Docker file in the repo. And then you expose the deployment, and it just works. Uh-oh, did I include the link here? I didn't include a link there. Oh, well, I guess take my word for it. I was going to show you a link to the logs. But the point being, if you have a TCP level load balancer, it's going to have no problems consuming the full bidirectional streams that we have with HTTP2. If you have any sort of HTTP specific or like layer 7 load balancer, it might become more difficult to work with gRPC because it won't know how to read the HTTP2, and it might do things like work in the case of a unary RPC, like our first 3 methods, and then it might fail when you have a streamed use case. We are trying to expand support in lots of different systems for gRPC because people very often, when they're developing cloud infrastructure, they'll think HTTP, I'm done. And we're trying to move things forward on that, evolve the thinking on that. Kubernetes is one of those cases. There are some efforts into serverless right now, and I think that those are good use cases for it. So we've done sort of north-south communications here, right? Like you can make a request from outside of a data center into a data center, but it's actually more common to do sort of east-west communications where you have 2 instances already in the same data center and they communicate with each other. We have great support for distributed tracing. Actually, that's one of the biggest things. Go has a concept of context that gets plumbed through and you just sort of manually pass it along the stack. A lot of other languages don't have that. And so gRPC will provide a concept of context that allows you to, say, initiate a request from a Python client outside, send it through to a Golang server, which is just like a stateless work transformer, pass it through to a database written in C++ using gRPC, and then the whole stack comes back. And you'll be able to get a full distributed trace of that in, say, like Google Stack Driver. Middleware is involved in that. OpenCensus is usually the most supported for it, but there are others that will work as well. All right. Does anybody have any questions about any of that? Nope.
Sorry, I muted you midway through because we heard a wicked echo. So.
Oh, no worries.
Questions? Anybody?
Thanks for opening the show. It's not a disaster. Yes.
Okay. Has anybody here actually ever used gRPC before? One person halfway? Okay, interesting. Hopefully you'll give it a shot now.
I used protobufs and
Gotcha. So I actually, before I joined the gRPC team, this was like back in college, I was working on like an autonomous robot. And one of the things that we did was we used protocol buffers as an interface definition language, and then we used WebSockets to stream from like a laptop to the robot. And I think that was right around when gRPC was coming around. I would say if you want to use protocol buffers, gRPC is the easiest way to do it.
I guess my question is, with every other network communication that I've ever dealt with, you end up having to know about how it's.
Sorry, can you like come closer to the mic?
Can you stand up and talk to him? Sorry.
No worries.
Yeah, so I guess for any non-trivial application,
Uh-huh.
with any kind of like remote call, so Java RMI, SOAP, REST, whatever, you ended up having to know a bunch of garbage about how it was implemented in order to really make it go in like a reasonable application. How far into the weeds do you find yourself getting for gRPC as opposed to like having to know about the transport layer?
Okay, so you're saying for RMI and for those other mechanisms, you have to know about the internals of the transport of the messaging system. For gRPC, the intent is that you will not have to know very much about it at all. I thought you were actually going with a different question. Generally, I don't have to know too much at all when I'm debugging gRPC services. It is relatively standard, like TCP. It tries to be not very opinionated about your APIs and about your transport, other than what you encode into the protocol buffer.
And so going back to also not really liking mocks, but I have found it useful at times to just record network traffic and play it back. Do you see anybody doing that kind of thing in gRPC implementations for testing?
Record traffic and play it back. Yeah, absolutely. That is a use case. I don't know of any open source tools that do that, but that is definitely something that is done internally to Google. And I don't think it would be too difficult to write a one-off tool to do that yourself. It very well could be something that we implement ourselves in the not too distant future. So it's good to know there is a GitHub organization called gRPC Ecosystem, which includes things besides just the language implementations. So there's like a gRPC web gateway proxy that exists there, and a lot of tooling exists there that you can look at. And I think replay is one of the use cases that would be served there.
Step on up. Approach the workflow. Approach the laptop. Speak into the microphone clearly.
Oh, mighty wizard. So can you speak to the two other questions that I have about gRPC? One of which is Twitch made twerp because they had some issues that they saw with adopting gRPC.
Mm-hmm.
And I'm curious if those issues are still relevant and salient, or whether that is really kind of a thing of the past. And the other issue is, how is the status of people who are trying to implement gRPC in the browser to be able to talk from the front end to the back end?
Right. Okay. Yeah, let's deal with those two separately. Can you first clarify what were the issues that Twitch saw when they implemented twerp?
So I think that one of them was that there was, when they were having problems with the upgrade path, so that, for instance, when there was a new version of gRPC, that they had to have all of their services had to actually all upgrade it kind of at the same time. Which they found problematic to do.
Right.
And then I think also that gRPC was using HTTP 2, and they made it so that they could run on HTTP 1 point whatever, so that they could actually sidestep some of the issues with like some of the places where that the ingress controllers and things that didn't support it. and
Okay.
such.
Okay. So let's deal with. I'm hearing like kind of 3 questions here. So the first question is about upgrade paths. So that could be talking about 2 different levels of interoperability. One is interoperability of the gRPC runtimes at different versions. We aim for 100% interoperability between different versions of gRPC. Since we hit 1.0, we have never major revved. And even before 1.0, the only reason that we broke wire protocol was because the HTTP2 spec was still evolving. So that's one part of it. That should not be an issue. And unless they were using things before the HTTP2 spec was complete, that shouldn't have been the problem. The other half of it is, what about backwards compatibility of the APIs that you write? Okay, so protocol buffers are an interface definition language. And the aim is that by writing a schema, you should get backwards compatibility. And that is a little bit of a dream, right? So APIs are things beyond just the types, just the shapes of your messages. It's also things like if 2 fields are mutually exclusive, right? So it's actually a linter error if you do not put a comment on every single field, every single message, every single service. And the aim is that you encode your full API contract beyond just the types in messages or in your protocol buffer. And those comments are actually transferred from your .proto file to your generated code. So there are best practices associated with not having outages when you upgrade your APIs. I mentioned one of those, wrapping your requests in a message that may actually just have a single field. In the future, it may not. You need to think about backwards compatibility whenever you are defining your APIs. And it turns out that it's actually a really difficult problem, but it's not something that is specific to gRPC. It's something that's fundamental to software engineering. So there's a saying here at Google, which is the more senior you get, the more time you spend designing protocol buffers, because it turns out that they're the hard part. Once you write your protocol buffers, including not just the types of messages and the fields they contain, but also the semantics of your full API, the rest of it sort of goes relatively smoothly. The other thing that they say is when you're reviewing code, you should start by looking at the interface, which is usually a protocol buffer. Then you look at the tasks, and only then do you look at the implementation. So I'm not saying that it's simple, but having backwards compatibility fully is not something that's just going to be within gRPC. Whatever system they switch to, twerp, I guess you called it, is either not going to be schema'd or it's going to be subject to the same problems when you do an upgrade. Okay, so I think that answers your first question about upgrades. The second question was web, gRPC web, which that's a great question. Okay, so we run on HTTP2, right? And there's a full HTTP2 spec which we conform to the T, and we make use of a feature called trailers. Lots of browsers, including Google Chrome, do not implement the trailer feature of HTTP2, which means that full streaming does not work. That feature of gRPC does not work. So I think it was around a year ago, and we made like front page of Hacker News for this. There was this project called gRPC Web, and the idea was we're going to write a different wire specification that encodes a subset of the semantics of the gRPC protocol, and it will get you definitely unary RPCs, and I want to say client streaming server unary RPCs. So there is a proxy that you can run that will translate the gRPC WebWire protocol to the gRPC full protocol. And what you would do is you would have that sit like very near to the front of your distributed system, and you'd run full gRPC within your data center and then gRPC web on the outside. Now, the ideal outcome here is eventually browser implementers implement the full HTTP2 specification, and also intermediary proxies like routers, L7, load balancers. They also implement the full HTTP2 spec, at which point the problem goes completely away, right? You can just use full gRPC anywhere. So there is a problem here, and it's one that we've like tried to dump capital into getting browser implementers to make it happen, but that fundamentally is the issue there. And gRPC Web was a way to mitigate it and to have an answer in the short term rather than the long term.
Okay, but that's so how mature is gRPC Web? I heard that there was so it existed, but it's fine and production ready and such, as far as you know?
Yeah. It's been around for over a year now.
Great.
And I'm fairly certain that people are using it in production.
Okay, cool, thanks. Anybody else?
Good questions.
Thanks.
Any other questions? Any other
Yes.
thoughts? I have that one.
Not necessarily specifically about gRPC, although it comes into play with you're talking about how like protobufs make it easier for you to extend and they're backwards compatible. Are there any best practices that have been built up for the case where you've been extending and slowly also hopefully deprecating some of these old fields, and now you've got a protobuf that has 40 fields in it and you're only using the most recent 10? Like, how do you have any best practices around safely actually cleansing that and doing, like garbage collection, for lack of a better word?
So, no, actually. Very often, so no, but also it's not necessarily a problem, right? So within the protobuf wire protocol, it's very much like key value pairs where, let's see. Okay, so it's very much like key value pairs where the key is the field ID and the value is the value of the field, right? And so if a particular key does not show up in the message, it's assumed, well, it varies between Proto 2 and Proto 3, but you can treat it like it's not there. So suppose over time you find that like in your original protocol buffer, you included an authentication string that you needed at that point. But over time, that authentication format, that protocol just like goes away completely and it's never needed again. It doesn't necessarily need to be in the message, right? And so at runtime, you're not incurring any cost from it. However, you might say like, hey, my protocol buffer is really messy because they're here. You could, so technically speaking, it's not considered the same protocol buffer. You forked it when you remove a field. You can do it, and it might mostly just work. But we found that oftentimes, even if you have a monorepo and you look at all instances of a usage of a particular proto, and you've removed all of them atomically in a single change list, you may still cause an outage because there are intermediary proxies who have cached the value of a protocol buffer message. It's not stored in code anymore. It's just cached in memory and the service is still running. They send a message to a service that now has no memory of that particular field and it goes, whoa, unknown field. And so there are different ways to define what you do when you see an unknown field number. But one of those modes, one of those handlers is crashing, which can be disastrous, right? So it is a very dicey idea. It might work in a small organization, but it's a really, really risky move for something whose value is, it's a little bit easier to read the file. So very often you'll see like there are a ton of fields in here that aren't used anymore. You might just like fence them off with a comment that said, these fields are deprecated, please do not use them, or something to that effect, right? And there are definitely protocol buffers that have existed at Google since, well, around when Google started, and that has not become like a practical problem yet to the point that a feature has needed to be developed where we, definitively deal with this problem. I'm not necessarily convinced that there is a full answer to this problem that will 100% guarantee that you don't cause an outage.
Because the flip side of that is keeping them around that would be attack surface for application DOS attacks. Because you have all these old fields.
Sorry, I'm not.
So,
is that something important?
Do you want to say that out loud?
I'm missing that.
Something I think about.
Well, I feel rude. So someone actually had an idea of if leaving those fields in the message could be larger attack surface, I think you
For
said?
application, it's not a gRPC related question. It's the same thing if you have like
An API.
HTTP endpoints that
Yeah.
you just don't use anymore, but they have to be there. Like, what happens when requests come in? You go, our developers have to touch that. The guy that wrote it is gone. Like, we don't know. What happens when somebody, figures out a buffer overflow for it?
Okay, so the question is about attack vector. So how does that present in attack vector, are you saying?
So that wasn't actually a question. We were just more musing about the fact that even in like generic HTTP APIs, a lot of the time you'll have, dangling code that you leave there. And
Right.
like in some cases, it makes a larger attack surface. So it wasn't that much of a question. It was just
Sure.
commentary.
Sure. And definitely there needs to be some sort of logic that does something about the fact that those fields might be present in a message that you get. It might be as simple as reject the request if it comes, but don't necessarily crash the server, right?
I think we have time for one more, if there is one more. Bob, do you have a question? Sure. Approach. You'll be the final question of the evening.
Okay, so I know when it comes to like Kubernetes and ingress controllers and things like that, HTTP2 and gRPC is a problem. It's problematic. I know Envoy can actually like route traffic based on RPC requests instead of TCP like connection stream. Is there any besides Envoy? Do you know of like any other ingress controller or anything that would be like Nginx can?
Yeah.
As an ingress controller?
Yeah.
I mean, Richard, do you have any thoughts on this?
So Nginx, I'm fairly certain Nginx will work. Originally, the gRPC web gateway was written as, I think, an Nginx plugin, but definitely Envoy is the most standard. There are also other things on that front in the not too distant future that I can't really talk about.
Noted.
All right, with that, Richard, thank you so much. This has been awesome. Thank you all for coming out.
Yeah, thank you. Great. Thank you.
Thank you.